So we're going to talk about comparison tests for series, and so specifically we're going to talk about the direct comparison test and the limit comparison test. So you might remember these from integration. So they're actually kind of the same thing. So I'll show you the first one, so the direct comparison test. So instead of talking about integrals now, we're talking about series, but I've got two series. So this a sub n and this b sub n series, a sub n will be less than b sub n for all n. Okay, so the direct comparison test says if the sum of b sub n, the series b sub n converges, then a sub n converges. If a sub n diverges, then b sub n diverges. So you've got to pay attention to this order here. Okay, so I think it would be easiest if we just look at an example of this. So we're going to use the direct comparison test to determine convergence for this series, n plus 2 over n squared minus n. Okay, so one thing that can be tricky sometimes is figuring out like what's a good thing to compare this to. And so for me, what I usually like to do is I like to look at just what are the dominating terms, which is another way of saying the terms of highest degree on top and on bottom. So these right here are going to be your dominating terms. So if I focus on those, so if I compare this series with just the dominating terms, n over n squared, well, you can see, right, that this will simplify to 1 over n. So what I want to do first is I just want to think about what happens with this series of summing up all the terms 1 over n. Well, this is just the harmonic series, so this diverges. So I am comparing this with a series that I know diverges. Now, the only other thing with this, though, is how do these two things compare? In other words, which one of these is bigger? Is this bigger? Or is this bigger? Because that matters for our test, right? So we're going to compare these two series, and I'm going to show you now, if you're looking at this and you're like, I can't tell which one is bigger, you can build up a comparison just step by step. Okay, so what you want to do is, the first thing that you want to do is just compare the denominators. So looking at this, I know that n squared minus n is going to be less than or equal to just n squared, right? And this is true because I know that my n's are greater than or equal to 2. So this is definitely true. Okay, so if this is true, then if I flip everything, then I also have to flip the inequality sign. So if this is definitely true, then this is definitely true. And so then from there, if I multiply both sides of this inequality by n, well, now you see how we get to the thing that we compared to, right? So if I compare this, I've got this whole series here, and if I just add 2 to this side, right, this is going to be bigger than this, right? So I just added 2 on top. And then this we already established is bigger than this. And this is ultimately just 1 over n. So you see how we can kind of coax out a comparison? So that's kind of what we wanted to do. And so what ultimately this says then is if I just reverse the order, so notice now I've reversed the order of the inequality, and I've just taken this part and this part, what I've ultimately shown is that 1 over n is less than or equal to n plus 2 over n squared minus n. So you can kind of slowly build this up if you're not sure how the order of this works. And so now I can go back to what was the direct comparison test. So remember, it's all about this here, and I have now, I've written this that 1 over n is less than or equal to n plus 2 over n squared minus n. So this is the order that I'm going in. And so then by the direct comparison test, since this diverges, then this diverges. So we've just proven that the series in question diverges. So that's how you can use them. The other test that I want to talk about is the limit comparison test. So again, we're going to have two series, a sub n, b sub n. So the limit comparison test actually has 3 parts to it. So I'll go ahead and just show you the 3 parts. You can pause here and read this first statement over. These are just the conditions, and then I'll show you the three parts of the test. So here it is. Okay, so the limit comparison test, we take two series, a sub n and b sub n, and we divide them, and then we take the limit as n goes to infinity. So if I do this, a sub n divided by b sub n, I do this and the limit comes out to a number, some number c, then either both series converge or both diverge. So we'll take a look at that in a second. Let's say that I evaluate the limit and the limit of this is 0. Okay, so then you have to know something about b sub n. So if b sub n converges, then you can also say that a sub n converges. And then finally, for this last limit, so if the limit equals infinity and your b sub n converges, then a sub n converges. So a lot of times what you're going to be doing here is you're going to be dividing by another series that you want to compare to, or you want to use to help you figure out what's going on with the original series that you can't figure out if it converges or diverges. So I think this is easiest if I just show you an example. So let's jump into it. Okay, so we're going to use the limit comparison test now to determine the convergence of 2n plus 3 over 5n plus 4, all of that to the n. Okay, so once again, just to come up with a series that is maybe a little easier to work with but related to the series that we're starting with, I just want to look at the dominating terms here. So inside the parentheses, that's going to be this 2n and 5n, all of that to the nth power. So what I want to do is I want to compare this series with 2n over 5n to the nth. So if I simplify this, right, so now that I'm looking at this, I can also see, right, I can cancel out the n's. So this is really just 2 over 5 to the n. And so looking at this, so this is a little easier to work with than the original series, and I can make some conclusions about convergence if I wanted to, but we're using the limit comparison test. So what I'm going to do is I'm just going to note to myself before I get too far in this. So this series is convergent. It is a geometric series. So I know this in the back of my head. So this series converges. So depending on what happens when I divide this series by this series, that is going to hopefully illuminate whether both converge or both diverge. So let's jump into this. Okay. So this is going to be a little bit of a journey now in terms of algebra. So I'm comparing these two series, and so I've got the original divided by the one I'm comparing with, right? And basically now what I need to do is I just need to do like a ton of algebra. So the easiest way to start this, and this is actually part of the reason why I chose a very similar series to my original one. So since these are now both being raised to the nth power, what that allows me to do is just rewrite all this stuff in here, all of it to the nth, because they're both to the same power. Now, this is a little bit of heavy lifting with the algebra. So what I want to encourage you to do is I want to encourage you to pause the video and try to see how far you can get with this. Because if I just show you the algebra, you're going to go, oh, sure, that makes a lot of sense. But if you actually pause and try to work it out on your own, even if you're struggling a ton, this will hopefully make more sense because the algebra is heavy lifting, so you actually want to think about it a little bit. So what I want to encourage you to do is at least first just start by, getting rid of the fact that this is a fraction over a fraction, see how far you can go with that, and then hit play when you think you've hit a roadblock. Okay, so what I want to do is I'm going to show you guys just kind of how I go through this. So I've got this divided by this fraction, so this divided by the fraction in the bottom, which means that, sorry, just making a little more space. So I've got this divided by this, that is equivalent to flipping the second fraction right and multiplying by it. So I can now go ahead and multiply the top and the bottom by 5 and 2. And so what I'm going to get now is, so 2n times 5 is 10n, 3n times 5 is 15, and then the bottom, multiplying all this by 2, I get 10n plus 8. Okay, so at this point, now I notice that I get something that says infinity over infinity, and that is all to the infinity power. So this is one of the indeterminate forms, and so at this point we can use L'Hopital's rule to help us determine the limit. So since I do have an indeterminate power here, that's going to be a certain application of L'Hopital's rule. I would strongly recommend, once again, this is a great point to pause and see how well you remember this and see if you can finish the limit, and if you get stuck, you can hit play for some hints. Okay, so I'm going to use L'Hopital's rule. To start this, the first thing that I've got to do is I've got to take the natural log. And in taking the natural log, what does that allow me to do? That allows me to take this exponent and drop it in front. And so then what am I left with? I'll clear some space in a second. So I bring the n down. And okay, so here's where I'm at. So if I think about this now, I've now got this infinity times whatever's going on here, so like an infinity times an infinity. This does not allow me to go any farther. So this is one of those cases then where you might need to manipulate the limit to use L'Hopital's rule. And so how do we manipulate the limit? There's a really standard trick with this where I take this n here, and now I write it in the denominator as 1 over n. And okay, so now I have this in the form, and I can move forward with this. Now I can apply L'Hopital's rule. So I can take the derivative of the top and the bottom. So this is kind of a harder derivative, but I want to recommend that you try to go through and find the derivative and just work through all the math on this, and then hit play when you're ready. Okay, so if I take the derivative of the top, so this is going to be the natural log, so that's the outside function, 1 over this times the derivative of the inside function. So we've got to use the chain rule. And the derivative of the bottom is just what you see here. Okay, so now I need to clean up all of the algebra on this, right? So there's a lot of algebra to clean up. So the first thing that I'm going to do, I'll just clear a little space. So the first thing that I'm going to do, I'm going to take this fraction and I'm just going to rewrite it flipped. So all I did from this line to this line is I just flipped this fraction, okay? So now that I've got this written like this, I notice in multiplying this, I've got 10n plus 8 and 10n plus 8 squared. So what can I do there? I can cross out this 10n plus 8 and just decrease this exponent by 1. So let's appreciate all the things I can do next. So one, I can multiply just these two denominators, 10n plus 15 and 10n plus 8. These can get multiplied together in the denominator. And then what am I left with on top? I'm just left with this. Now, I want to make my life a little easier. So I notice I've got 10 and 10. I'm actually going to factor the 10 out of the top. So what does all of this look like when I do all of these little things? Okay, so out of the top, I've factored out 10. So I'm left with 10n plus 8 minus 10n plus 15. So I've still got to do this operation, and then I've got to multiply the bottoms together. And I've still got this fraction in the bottom. So what I want to do now is I want to make this all just one solid fraction. So what am I going to do? I am going to distribute this negative sign here, and then this fraction, I will just flip it so that it comes up like this, and now I can finish all the math up here. So now I can see that the 10 n's are going to drop out, so I'm left with 8 minus 15, which is negative 7, all of that times the negative n. So here's everything that I'm left with when I complete this operation. I've got 10 times negative 7 times negative n squared, all of this times the denominator. Okay, so now the top becomes just positive 70n squared, and I've still got the denominator. So next I'm going to multiply all of this stuff in the denominator together. So now I've got 70n squared over 100n squared plus 230n plus 120. And so now I've got infinity over infinity again, right? So I've got to use L'Hopital's rule. So like I said, this is a journey with the algebra. So I go ahead and I take the derivative of the top and the bottom. I still have infinity over infinity in this case, 140n over 200n plus 230. So I take the derivative one more time, and I'm left with now 140 over 200. And so this, now if I take the limit as n goes to infinity, this is just a constant, and so this will simplify to 7 over 10. Okay, now remember, I started this whole problem by taking the natural log of it. So whenever you use that trick, after you find the limit, you always have to raise that to e. So this is going to be e to the 7/10 as my answer. Okay, so now for that part where it's like, what were we even doing, right? So, okay, so remember, we were working on the limit comparison test, and I had this a sub n divided by b sub n. So which one of these three conditions have I met now in the limit comparison test? I have met the one where this has converged to a certain value. So we're talking about this condition here. So I have found now that this crazy limit that I had converged to a value. So what this means is that either both series converge or both diverge. And you'll remember that when I started this, I chose a series that I know converges. So what that means now is I can conclude that both converge. And so that means that we have convergence here, so therefore my original series also converges. So sometimes when you're working through some of these, you can have a wild ride with some of these limits. Let's talk about one other one, maybe just with a slightly different result. So same idea, we're going to use the limit comparison test for 1 over the natural log of n from 2 to infinity. Okay, so in this case, as far as like what do we compare it with? So the easiest choice would be just to compare with 1 over m. And what do you know about 1 over n? Well, you know that this series is going to diverge, so we'll just remember that in the back of our head. So let's go ahead and let's just set up the limit, which is going to be much simpler than the last one. So I've got my original limit divided by the limit that I'm comparing with. So if I simplify what I've written down here, this becomes just the limit as n approaches infinity of n over the natural log of n. So I'll give you a second, or I would suggest that you take a second and you finish this and you draw your own conclusion and take a look at the limit comparison test and just see if you can figure out what this is going to equal. Hit play when you're ready. Okay, so this is infinity over infinity, so I can see here that I can just take the derivative of the top and bottom. So over here, so the derivative of n is 1, the derivative of the natural log of n is 1 over n, and all of this can be simplified again to just n, right? So 1 divided by 1 over n just equals n. So then, of course, as n goes to infinity, this just equals infinity. So now I have to remember what the limit comparison test says. So in this case, I've run into this third condition, right? Where now my limit equals infinity. So what does this mean? Well, I know that I chose a series to compare it with that diverges. And so therefore, my original series will also diverge. And so my conclusion here then is that our series diverges. And so that's going to be the way that you want to set these up. So when you set up your limits, try to choose something that is, you know, nothing crazy, something kind of similar to what your original series is, but something that you know whether it converges or diverges. Okay, and so that's the end of this video. So thanks for watching, guys. I will catch you guys next time.